In this video, I'm going to introduce the concepts for projectile motion. Let's start with the definition. What is a projectile? This is an object that is in the air. It is moving both horizontally and vertically, and is only acted on by the force of gravity. Here are three objects, all of which are in the air. The question is, based on the definition at the left, which of these would be considered a projectile? Well, it wouldn't be choice A, a commercial airliner. There are many forces on an airplane other than the force of gravity. Wouldn't be choice B. If we drop a rock from a window, we'd expect it to travel straight downward on a vertical plane. We'd want to pick choice C. A football thrown by a quarterback would be moving left and right and up and down at the same time. It'd be in the air, and the only thing affecting the ball after the throw would be the force of gravity. We don't consider air resistance for projectiles, much like we wouldn't consider them for freely falling objects. Once we identify what a projectile is, we can look at the path of it. We'll stick with that football being thrown by a quarterback. It's thrown up and to the right with an initial velocity vector. It's going to be moving in this parabolic shape. You'll be looking for that when you study projectiles. Diving in a little deeper, we're going to break this into two parts. We'll first talk about vertical motion, vertical velocity. Because this football is thrown up and right, part of that is directed upwards. I'm going to copy that as a vector at position A, call that VYO, the Y for the vertical part, and the O representing a time of 0 seconds, or the first moment we start to look at it. The goal here is to think about what the vertical vectors would look like at positions B, C, D, and E. Our options are to send arrows up or down to make them longer or shorter or the same length as the one at A. I'll talk you through each. At B, we'd expect it to still be upward, but just a little bit smaller than it was before. At position C, it's transitioning from moving up to down, so at that instant, we'd expect the vertical velocity to be equal to 0. At position D, it starts to move downward, and at position E, it's moving downward even faster. So notice that the vertical velocities are always changing, and the reason for this is because of the downward force of gravity. This force is always pulling downward, and it's making each velocity vector more negative than the one before it. Let's start over and let's analyze horizontal velocities. Again, this is thrown up and right, so part of this goes to the right. I'm copying that at position A. I'm going to call that Vx. Again, the goal is to track what the vectors would look like at positions B, C, D, and E. This one's a little easier to talk through in a sense that they're all the same. The velocity horizontally would be constant, and the reason would be because there's no horizontal force. After the ball is thrown, there's nothing pushing it forward to speed it up. There's nothing pulling it backward to slow it down. The only force we have is a downward one, and that's not going to affect the horizontal velocity of the projectile. All that together, we have a vertical velocity that's changing downward, and we have a horizontal velocity that's staying constant. We split these into their parts because independently they're easier to discuss. To do it all at once could be a little more complicated. Just know that these motions are independent of one another. Just because you change one does not mean that you change the other. Here's an example trying to explain that further about how they're independent. We're looking at someone sitting in a car. While the car is moving, the person has an object in their hand and they're going to throw it straight up into the air. And the question is, when the ball drops back down to the same height as the thrower's hand, where would it land? Would it land in front of the person by the front windshield? Would it land behind the person by the back windshield? Or would it land right back in their hand? Let's talk through it. A couple key moments. First is at the time of release. Note that everything's connected. The ball, the person, the seat, the car, everything is moving to the right with the same velocity. I'm calling that V car. Even though the object is thrown upward, the driver did not put a forward force on the object or a backward force on it, so there's nothing that has been done to change the horizontal velocity of the object. From all that, with nothing to affect the horizontal velocity of the ball or of the car itself, there's no reason for one of those to pull ahead of the other, and so we would select choice B, back in our hand. Even though the driver has changed the vertical velocity of the object, they've done nothing to change the horizontal, and we'd expect it to land right back in the hand. Finally, just want to talk through some graphs specific to this motion. We're looking at 6 graphs, 3 horizontal and 3 vertical. We're tracking position, velocity, and acceleration as functions of time. Consider our previous position A as the origin, 0, 0. If you want to pause the video and try to sketch these 6 graphs on your own, I'll talk you through them shortly. All right, let's start horizontally. We know it's moving in the positive direction, and we know that it's maintaining a constant velocity. So we have a linear graph shape for the position, a constant horizontal positive velocity of the v-graph, and no acceleration for something that is not speeding up or slowing down. Vertically speaking, we're going to have a parabola. This is, while moving up, decreasing its slope and getting slower, and increasing its slope on the way back down as it speeds back up. The vertical velocity, just look at the velocity vectors. Upward, positive, and a big vector, then upward, positive, and a small vector, 0, negative, small, negative, big. So I'm just connecting all of those with a straight line, and my acceleration is a constant negative value equal to negative 9.8 meters per second squared, the acceleration we'd expect on Earth.